Welcome back to the Explainer, folks. For all the marine engineers and navigators tuning in, you already know the deal. When you're operating offshore, the margin for error with heavy loads is, well, it's practically zero. Today, we're zeroing in on mastering offshore cranes. We're going to break down the hardware, the brutal physical limits you're up against, and those non-negotiable testing regimes that literally keep your crew alive and your vessel upright. Okay, let's get right into it.
I want you to really picture this scenario for a second. What happens when a 250-ton lift meets a 6-meter swell? We're definitely not talking about a calm day in port anymore, right? We're dealing with massive, unpredictable physical forces. A single drop of a wave can transform a totally static weight into a dynamic, structure-shattering threat in just a fraction of a second. Out here, thoroughly understanding your crane's effective use and its hard limitations is absolutely a matter of life and death.
So here is our operator's blueprint for the explainer today. 1. The anatomy of offshore cranes. 2. The physics of lifting. 3. Overcoming dynamic limitations. 4. Mastering simultaneous operations, or SIMOPs. And 5. Testing and inspection regimes.
Starting off with Section 1, Anatomy of Offshore Cranes. Let's look at the hardware built for this harsh environment.
Let's stack up the two main heavyweights side by side, the mast crane and the pedestal crane. Now, for the pedestal crane, which you've all seen a million times, that entire load moment is transferred directly through the slew bearing. That makes the bearing an incredibly critical, super highly stressed component. On the flip side, you have the mast crane. It transfers the load moment through its actual mast construction. This definitely saves wear and tear on the bearing, but the trade-off is you'll generally need a lot more headroom and a slightly heavier overall build. Understanding how these interface with the hull dictates exactly how you map out your deck space and maintenance schedules.
And your choice of boom? That completely dictates your operational limits. Take a box section boom. It gives you excellent flexibility and spring constant characteristics for bad weather, which means much better derating curves. But what if you need a reach over 40 meters? Well, then a lattice boom is way lighter, though it does require wire luffing and restricts you to mostly lifting from the tip. For serious offshore work, knuckle booms are just incredible because they drastically reduce pendulum effects by bringing the boom tip right up close to the load. And telescopic booms, perfect if you're tight on space and need compact stowage. It's all a calculated mechanical trade-off.
Moving into Section 2, the physics of lifting. This is where static loads turn into serious dynamic threats. Okay, the crucial mathematical reality of offshore lifting all comes down to the DAF, or dynamic amplification factor. This represents those brutal moments where external forces multiply a load's actual weight. It's defined pretty simply as the dynamic load plus the static load. But make no mistake, miscalculating your DAF is the absolute fastest way to capsize your vessel during a lift. It is, without a doubt, the single most important metric dictating your stability. So what's actually causing this massive spike in force? It's a really nasty combination of vessel heave, pitch, and roll. Mixed in is subsea currents and those intense hydrodynamic forces right in the splash zone. But you know the real nightmare scenario of physics here? The slack wire. Imagine a vessel roll causes the crane tip's downward velocity to outpace the load's freefall velocity in the water. Your hoist wire goes completely slack. And when that vessel violently heaves back up, bang, you get a catastrophic shock load that can easily rip the crane straight off its pedestal. Because of all that, there is obviously a night and day difference between harbor and offshore lifting. In a harbor, you've got a nice, controlled environment. Your maximum allowable hook load needs almost zero adjustment because dynamic force is practically non-existent. But offshore? It's chaos. High relative motion induces massive shock loads, which severely reduces your safe working load. You just cannot apply harbor logic to a subsea lift, ever.
Which brings us to Section 3, Overcoming dynamic limitations. How we engineer our way through the chaos.
All right, how do we fight back against the heave? We've got three main mechanical systems. First is constant tension. This maintains a preset wire tension just below the load's weight, keeping that wire taut so we avoid this dreaded slack wires we just talked about. Second is passive heave compensation. Think of this like a massive shock absorber. It uses the load's own motion to charge hydraulic accumulators and dampen the movement. And finally, the gold standard, active heave compensation, or AHC. This setup uses a motion reference unit to feed real-time vessel motion data right into the system. It basically allows for automatic winch control that essentially freezes the load in place relative to the seabed, totally regardless of what the ship is doing up top. But hey, even with top-tier compensation, there are still hidden traps, like seabed suction overload. Picture this. You're retrieving a subsea load that's penetrated the seabed, and it refuses to budge.
A sudden upward vessel heave could literally pull the entire ship over. To stop this catastrophic failure, operations where the breakout load could potentially exceed 70% of the crane's safe working load mandate the use of a specialized hydraulic cylinder device. This safeguard accommodates the upward motion of the vessel and protects the crane if the load just won't break free.
Section 4. Mastering SimOps. Simultaneous operations on deck and subsea. Running deck SimOps requires absolute flawless choreography. It always starts with a comprehensive job safety analysis and toolbox talk. Then you lock down primary and secondary comms. You set up hard visual barriers and clear out anyone who doesn't absolutely need to be there. And remember, there's only one conductor for this orchestra, the deck foreman. They tightly coordinate both cranes so those booms never ever cross paths.
Now, taking those SimOps underwater, that introduces a whole new layer of risk. You're basically flying blind down there, so you have to use subsea transponders on the crane wires just to confirm depth and position. You're also monitoring extreme weight shifts as loads punch through the splash zone, which means strict adherence to your anti-heeling pumps. And here is perhaps the scariest scenario. If both your heavy and light cranes are somehow connected to the same subsea load, you have to rigorously monitor tension. If that smaller 20-ton crane accidentally takes the full weight from the 250-ton crane, it instantly exceeds its safe working load, and you've got a major failure on your hands.
Finally, Section 5, Testing and Inspection Regimes, how we actually verify the hardware's integrity. This right here is the non-negotiable inspection timetable that every chief engineer needs to have burned into their brain. Before first use, foolproof load test. Then you've got your 6-monthly thorough examinations, your 12-monthly tests, and of course that massive 5-yearly proof load and thorough examination required by international classification standards. Plain and simple, if these checks aren't documented, that crane is not moving.
And when we talk about personnel suspension, man-riding, we're talking about human lives hanging on a wire. That makes this ratio 10-to-1 absolutely critical. For equipment that wasn't specifically designed purely for man-riding, maintaining a 10-to-1 safety factor is your strict baseline. It provides massive, essential redundancy for your brakes and winches, even if partial mechanical failures happen.
Now, all of these mechanical checks we've discussed, from testing the MRU to taking grease samples from the slew bearing, they are all governed by rigorous procedures. Strictly adhering to your company's lifting operation procedure isn't just about checking a box or pushing paperwork. It's literally the central nervous system of offshore safety. It separates routine lifts from non-routine ones, and it mandates the exact engineering checks that have to happen before the hook even leaves the cradle.
But despite all the incredible engineering, your ultimate safety mechanism is human. The bosun or the crane operator's decision to suspend an operation is final. If the weather suddenly turns, if a wire isn't spooling right, or if the load just feels off, the operator has the absolute authority to stop the job right then and there. Empowering your crew like that is the true bedrock of any real offshore safety culture.
So I'll leave you guys with this thought. We've covered the brutal hardware demands, the completely unforgiving physics of the dynamic amplification factor, the lifelines of heave compensation, and why we are so strict about SimOps and testing. The ocean does not care about a poorly planned operation. It will not forgive you. So the next time you approve a lift, ask yourself, is this plan built for a calm harbor, or is it truly ready to survive the dynamic realities of the ocean? Thanks for hanging out with me for this explainer. Respect your limits out there, and I'll see you on the next one.